right, so we're looking for those separable solutions. Make the Ansatz. Substitution. Ansatz. That's German. Makes the Ansatz into minus h bar squared over 2m rad squared psi plus v psi equals e psi to obtain, well, we've got the minus h bar squared over 2m out front, and then we're going to get y over r squared ddr of r squared d big R dr. So in other words, we're using the fact that the Laplacian is this expression right here. And if I feed capital R, capital Y into this expression, the first term differentiates with respect to R, so capital Y can be pulled out to the front of it because capital Y only depends on theta and phi, and therefore is a constant as far as differentiation with respect to R is concerned. So the capital Y pulls out front, and because capital R only depends on little r, these partial derivatives with respect to R become total derivatives of capital R because that's the only variable that it has in it. So that's what the first piece becomes with the minus h bar squared over 2m out front. And then we get plus, now for the second pieces, capital R pulls out to the front of those because it doesn't depend on theta and phi, which is what those differentiate with respect to. So for the other two pieces, we get plus R over little r squared sine theta, partial with respect to theta because y depends on both theta and phi, sine theta partial of y with respect to theta, plus, pull out capital R again in the third term, big R over cute little r squared sine squared theta, second partial of capital Y with respect to phi. So all that is the Laplacian applied to Ry and then multiplied by minus h bar squared over 2m. So that's the kinetic energy term, plus the potential energy term, which we'll just write as Vry. In other words, it's V psi, but psi is Ry, capital R, capital Y. So plus Vry, implicit there is that it's V of R theta phi, R of R, Y of theta phi, but you know, why do all that declaration? It's implicit, equals E Ry. Now so far we haven't separated anything because all three terms contain all the variables, but we can fix that. Because now we're going to multiply both sides by minus 2m little r squared over h bar squared capital R capital Y. So we're dividing through by psi, because that is capital R capital Y, and also, just to do some other simplification, as we'll see, we're multiplying all that too by minus 2m r squared over h bar squared, where it's little r squared. And what that turns this beast into is something I'm going to write over here because it's a long thing and I don't want to write towards the bottom of the board because I'm taller than it would be comfortable for that. curly brace, the curly brace is going to be because I'm going to say, oh, all this stuff only depends on R. So big curly brace, 1 over capital R, ddr of r squared d capital R dr, again, total derivative because big R only depends on little r, minus 2m r squared over h bar squared times v as a function of r. I don't have to put that as a function of r, but it's just to emphasize v only depends on r here. That's our hypothesis. We're just saying, let's suppose v only depends on r, minus e. So I pulled the e term over to the other side, plus 1 over capital Y, curly brace, 1 over sine theta, d theta of, actually I should say, partial with respect to theta. Partial with respect to theta of sine theta dy d theta plus 1 over sine squared theta, second partial of y with respect to phi, close big curly brace, equals 0. So I took the e side term over to the other side. And by dividing through by ry, notice when I divide through by ry, in the first term I get capital Y over capital R capital Y. So that cancels the capital Y's. And in the second two terms, I've got capital R over capital R capital Y. That cancels the capital R's and leaves only 1 over capital Y's. So that's why there's this capital R over with this term and a 1 over capital Y over with this term. And now we don't mix the radial and angular dependencies anymore. And part of that came from the reason why we multiplied through by this r squared here is because that would get rid of these little r squareds in the angular terms. And meanwhile, just cancel the 1 out here in the radial term. And so that completes the separation. And then the minus 2m over h bar squared is just to cancel out the 1 that's out in front to begin with. You just turn it all into a 1. All that equals 0. Okay, any questions? I should let people catch up with all that if they haven't yet. And then we note that that first term only has things that depend on r in it. E is a constant, but that's okay. I can still say it only depends on r. And the second term only depends on theta and phi. So I have separated out the radial and angular dependencies. I've made it a sum of a term that only depends on r and a term that only depends on theta and phi that has to add up to 0. Okay. Questions? Happy or like you're a little bit concerned? Yep. Okay. Anybody concerned? Or is everybody feeling as joyful right now as I am? Come on, work with me here. Come on, humor me.
Yay.
There you go. All right.
Okay, I'm joking. There you go.
Yeah. All right, I feel sufficiently humored. And there was much rejoicing. Because they
theta and B and I.
Yes, that's right.
Isn't it?
Now, what we're going to argue is that in fact, not only does this only depend on R, it doesn't depend on R, it's constant, and so is that term. How are we going to get that out of here? If I move along a radial line, so in other words, I picture myself, I start out at some point and I just move straight outwards away from the origin from that point and sample. Here I go, sampling function, I'm a little fly, sampling the function as I move. The first term could change in principle because for all we know it would appear it depends on R. But the second term cannot change. Why can't the second term change if I move along a radial line? Whoops.
The angles are the same.
The angles are staying constant, that's right, yes. Since theta and phi are not changing, the second term can't change because it only depends on theta and phi, but those are staying constant. But the sum has to stay constant, namely it has to stay 0. The sum has to stay the same, namely 0. So the first term actually has to be constant too. The first term must actually also be constant along my radial line. So therefore, the first term actually is a constant. In principle, it looks like it depends on R, but in practice, it's actually a constant. It doesn't even depend on R. Or in other words, the different R dependencies in it cancel one another out, is what happens. Questions? It's crucial to understand this point. Similarly, I want to show that the second term is also a constant. How would I do that? Well, before I moved along a radial line, what do I want to move along this time? Yeah, I want to move on a surface of a sphere of constant R. So it actually doesn't matter the details, I just have to fly along a sphere of constant radius. Doesn't matter how. How am I going to do it? If I move along the surface of a spherical shell, of constant R, the second term might change, but the first one doesn't. So therefore, the second one doesn't either. So those two arguments together show the two terms are actually both constants. Moving along a radial line shows the first term is actually constant because the second term is, and they have to add up to 0 at all points. flip it around, all around a spherical surface of constant r, second term could in principle change, but the first term can't because r is constant on such a surface. Therefore, the second term being constant implies that the first term is constant, and QED at that point. Quite easily-ish done. And furthermore, the constants have to be equal and opposite one another because they're adding up to 0. So that means, in fact, we can set each of those terms equal to a constant and then solve. So that says then that 1 over r ddr of r squared d capital R dr minus 2m r squared over h bar squared times v of r minus e is equal to a constant, and naturally we're going to call that constant little l times little l plus 1. You're like, what? Naturally, yes. However, you may recall that the eigenvalues of the angular momentum operator are L plus 1, h bar squared, and that's what's going to come out of all of this. So in other words, we are accepting the wisdom of those who have gone before in saying the constant is little l plus 1, because that turns out to be the best thing to call. So no, you wouldn't say, the first person who solved this didn't say, I'll call it little l plus 1. No, they solved it and then said, I should have called the separation constant little l plus 1. So that's what we call the separation constant. But notice, we haven't assumed anything about V except spherical symmetry. So in other words, this isn't particular to hydrogen. It's going to be true for hydrogen, but it's true for any spherically symmetric potential energy function. Inspiration, the angular momentum squared eigenvalues have that form, that they're L plus 1 h bar squared. We don't know that yet. Well, we know that. That's why we're choosing that. And then also, 1 over capital Y times that beautiful mess, 1 over sine theta d theta of sine theta dy d theta plus 1 over sine squared theta second partial of y with respect to phi. All that has to be minus l plus 1 because the first piece was l plus 1 and they have to add up to 0. So now, all we have to do is solve those two equations and we're golden. So we'll talk about solving the first one. No, talk about solving the second one, comma, first. And then, for the other piece, well, that's going to depend on the form of V of r. But again, notice this equation is independent of the form of V of r because it doesn't contain V of r in it. So it's in common for all spherically symmetric problems. Angular momentum. We'll show that the operator, which represents the total angular momentum squared, squared times this differential operator. 1 over sine theta, partial with respect to theta, of sine theta partial with respect to theta, plus 1 over sine squared theta, second partial with respect to phi. Huh, does that look familiar? Why, yes it does. It would be the beast that's over in brackets there multiplied by minus h bar squared. So I'll just say, note what's in the brackets. Come and get it. Hungry already. Why, I'm positively dizzy as I spin around thinking about this angular momentum operator here. So the angular part of the wave function satisfies L squared y is equal to L plus 1 h bar squared y. Because notice over there, I could take that second equation over on the left board and write it as brackets equals minus L plus 1 y, and then if I multiply those brackets by minus h bar squared, then I get brackets equals L plus 1 h bar squared y. But those brackets we're claiming are, the stuff in brackets is the angular momentum squared operator. So this, if now I attach the theta and phi to remind ourselves that y is in fact a function, this says operator times function equals a number times the function. In other words, that is a what kind of equation? It's an eigenvalue equation, right? It's an eigenvalue equation. The eigenvalues of L squared are of the form L plus 1 h bar squared. We don't know what L's are yet. We'll later find their integers, but we're not there yet. They're of the form L plus 1 h bar squared. And the y's we seek are eigenfunctions of L squared. Now, it certainly wasn't obvious the first time that the Laplacian was written in spherical coordinates that the angular part of it had anything to do with angular momentum. And yet, apparently, nature thinks that would be a really cool idea to make that differential operator have a lot to do with angular momentum. So, wow. Yes?
Who thought of these ideas first?
Well, I'd have to look up the history. So I'm not sure, who first did the separation. It might have been Laplace. I don't know. Alex, do you know? You know a lot of these kinds of things. Okay, even Alex doesn't know. Okay, I feel better now. But this goes back to a point I've made before, which is sometimes students get the impression that it was quantum mechanics that inspired physicists to realize that some systems are quantized. But that's not it. That's not how it worked historically. Physicists had long known that wave equations coupled with boundary conditions produce quantization. In other words, physicists had long realized that if you shake a string and tie off the ends, that only certain number of wavelengths can fit in between and have it have a well-defined sinusoidal time dependence. So the boundary conditions of vanishing on the end leads to normal modes, leads to quantization of the wavelength on the string.
And so an octave as a unit.
Yeah, you do the octaves in music and all that kind of good stuff, right? Yep. Because the second harmonic has double the frequency of the first harmonic, so they differ by an octave. And that's if you make a musical scale that has 8 tones in it. You know, there are other musical scales that don't. In any case, it was known for a long time that the vibrations of a stretched drum head have Bessel functions as their shapes, because there you've got boundary conditions that it vanishes on the edge of the drum head. So there are lots of examples of quantization from wave equations. Then experiments started to show that matter often exhibited quantization behavior, that there were discrete energies and so forth. And so knowing what they already knew about wave equations producing quantization perfectly classically, nothing quantum about it, that was the inspiration to say, hey, let's try to make matter be represented in terms of waves, because we know that if we can put boundary conditions on the matter waves, we'll get quantization conditions. And Schrödinger is the one who had the insight to invent the Schrödinger equation, which ended up being able to explain the hydrogen spectrum. But it's not that he wrote down the Schrödinger equation and discovered, holy crap, it has quantized solutions. It's he wrote it down because he was trying to explain the observed quantization of the hydrogen spectrum via a wave equation with boundary conditions applied to it. So historically, the physicists already knew they ought to be able to get a wave equation to have quantization, and then Schrödinger is the one who won the race to come up with a suitable wave equation. He thought he was describing the charge density of the electron. He wasn't at all happy when the interpretation became in terms of psi squared being probability density as opposed to simply charge density. Schrödinger invented Schrödinger's cat to try to prove that the probabilistic interpretation of the solutions of this equation couldn't possibly be right, because Schrödinger's cat's ridiculous. It didn't work. He didn't convince anybody that way. Just like Einstein invented the EPR, Einstein, Podolsky, and Rosen invented the EPR paradox to prove that because it's ridiculous that the wave function could collapse instantaneously, it must be quantum mechanics can't be a complete description of reality, and that didn't work either, because later it was shown by Bell that that makes different predictions than what are so-called hidden variables theories, local hidden variables theories. And all the experiments so far have decidedly ruled in favor of quantum mechanics. So Einstein, Podolsky, Rosen, and Schrödinger all invented paradoxes to try to prove that quantum mechanics can't be right, and all they did was help to further demonstrate that quantum mechanics appears to be right. So that's how these things often work. But that's what science is about. You try to knock your theories down. You don't just say, oh, that's so beautiful, it has to be right, now we're done. You try to knock it down. And sometimes the theories say, give it your best shot, I'm back up again. And so they just punch out the people that came up with the paradox, and too bad for them. All right. So now our job is to figure out what L is. What are the allowed values of L? We're going to do that. But it's going to take a while. So classically, L is R cross P, right? With respect to some origin, the angular momentum vector is the position vector across the momentum vector. It's origin dependent, but given an origin, given some origin of coordinates with respect to which I'm calculating the angular momentum, if I've got some particle with momentum P at a vector displacement R from the origin, R cross P is what I calculated in order to get the angular momentum of that particle with respect to that origin. And then, like any self-respecting dot product or cross product, and even ones that don't respect themselves, I can expand that out as a symbolic determinant. I put x hat, y hat, z hat along the top row. The components of R along the middle row. What are the components of the R vector? X, Y, Z. Yeah, X, Y, Z. And the components of P are piece of X, piece of Y, piece of Z. So we'll expand this out, and then we'll say all we have to do to make the quantum mechanical angular momentum operator is to replace px, py with pz with minus ah bar ddx minus ah bar dy minus ah bar ddz, and take that symbolic cross product. So if I figure this out, well, it's the usual thing. I start with x hat, and then I find the determinant of the submatrix that I get by crossing out its row and column. So I get x hat times ypz minus zpy. And then for y hat, I have to take the determinant in the reverse order because there's a minus sign in front when you go to the next column. So for y hat, I get y hat times zpx minus xpz. And then for z hat, the z component, I get xpy minus ypx. So classically, that's an expression for the angular momentum in terms of the components of the position vector and the momentum vector for the particle. Okay, any questions? So then, time to go to quantum mechanics. In QM, we thus get in the coordinate basis that the Lx operator, as an operator, will be y operator, z momentum operator minus z operator, y momentum operator. So I'll use capital letters to say operators in the abstract. So ypz minus zpy. And then if I go into the coordinate basis, I just make the usual substitutions that y and z are simply little y and little z, and the momentum operators are derivative operators. So this becomes equals minus IH bar y partial with respect to z, so y times minus AH bar ddz minus IH bar z ddy, or in other words, plus IH bar z ddy, which is equal to minus IH bar times the quantity y ddz minus z ddy. So in Cartesian coordinates, the x component of the angular momentum operator is minus AH bar y partial with respect to z minus z partial with respect to y. So it's eigenfunctions of that operator, which will be wave functions with a well-defined x component of the angular momentum. And then notice the pattern there, that you start with coordinate derivative, first coordinate derivative of the second minus second coordinate derivative of the first inside parentheses, which lets us write down what the other ones are. So the Ly operator is zpx operator minus xpz operator, and following that pattern, that's minus IH bar, and then in parentheses, z ddx minus x ddz. So eigenfunctions of that operator will have well-defined y component of their angular momentum. And our personal favorite, the one that we'll come back to over and over again, although we'll write it in spherical coordinates because it's actually quite simple in spherical coordinates. Lz is xpy minus ypx. So that'll be represented in a coordinate basis as minus IH bar x d dy minus y dx. Just for fun, notice that in fact we can write this as a vector operator. L equals x hat, y hat, z hat, x, y, z, minus IH bar ddx, minus IH bar ddy, minus IH bar ddz. What I said before, you just plug in the operators for px, py, and pz, and symbolically, that's equal to minus IH bar times x hat, x vector cross grad. So in other words, you can take a symbolic cross product of x, well, we call it r here, so I'll just leave it as r again. It's a symbolic cross product of r cross the gradient operator times minus IH bar. Which kind of makes sense because, in other words, that's r cross minus IH bar grad. But minus IH bar grad is the momentum operator in the coordinate basis. Two, four, six, eight. It's now time to commutate. Once again, we don't want these operators to necessarily just sit at home. And now it's time to use all the fun things we've learned about commutator identities. Ooh, this is going to be good because while you could throw a test function at these things in order to work out the commutation relations, it's easier to do it all algebraically. So what, pray tell, is the commutator of Lx and Ly? Well, again, you could throw a test function in. Ouch. Let's not do that. Let's do this. The commutator of Lx and Ly is equal to the commutator of, all symbolically, just in terms of generic operators, no particular representation needed, ypz minus zpy. As an operator, that's what Lx is, commuting with zpx minus xpz. Now for that, we can do all kinds of cross product terms here. So in other words, what this is all the possible ways these guys can mix it up. So in other words, it's the commutator of ypz and zpx. So what we get from the first terms there, minus, now I will do ypz and xpz, ypz and xpz commuting. That commutator. So that is coming from ypz and xpz, these two terms right there. And then there's a term for this pair and a term for this pair. So then there's also minus zpy commutator of zpy and zpx. And then plus commutator of zpy and xpz. So that breaks into 4 commutators. y commute with pz? Remember our commutation relations. Go back to the beginning. Does y commute with pz? Yes, it does, because pz is I minus ih bar ddz. So it doesn't matter whether you take ddz of y times the function or y times ddz of the function, because to a derivative with respect to z, y just looks like a number. Y just looks like a constant. So these guys commute with each other. Does y commute with x? Yes, it does, because multiplication in the x base, on the coordinate basis, x times y is y times x. Does x commute with pz? Yes, it does. So all these guys commute with one another. It's a big, happy commuting family. Similarly over here, all these guys commute with one another. All these operators commute with one another. The technical term for that, of course, is they carpool. That means those two commutators go away. Because every term everything you form out of those is going to commute. It's going to be same forwards and backwards. So those terms go away. So now it's time to play pull the operator, right? Remember that we have these rules that said that you proved in a homework that if I have something like this commutator, AB with C, I can simplify that as pull the A to the left and pull the B to the right. So this is A times the commutator of B with C plus the commutator of A with C, pull the B out to the right. Let's prove that in homework, remember? Yes, yes. Okay, well, trust me, you did, okay? So you can do that with commutators. And it works the same on the other side, too. You can pull to the left, pull to the right. Pull the one on the left out to the left, then pull the one on the right out to the right. So that means we can go nuts with these remaining two terms. So this turns into the first term, pull the y, and I get the commutator of pz and zpx. Pull the pz to the other side, so I get plus the commutator of y with zpx pz. So I can make that first term turn into that. First pulling the y to the left in the first piece, then pulling the zpz to the right in that first term. Then I do the same thing to this term. Pull the z, pull the py, pull the z out to the left, so I get z times the commutator of py with x pz, plus pull the py out, commutator of z with x pz, with py on the outside. So I've done it on the first terms now. On the first term in the first commutator, I pulled y to the left, and I pulled pz to the right. In the last commutator, I pulled z to the left, and I pulled py to the right. Now, I can do the same sort of thing with the second terms. So, how much would you pay? Don't answer yet, because wait, there's more. So now I can pull out z to the left, so I get, and order's important, I'm pulling it out of the commutator so it comes right to the left of the commutator. So I get yz times the commutator of pz with px, what's the commutator of pz with, what's the commutator of pz with px? 0, because remember, the x's and the x operate, the x, y, z, px, py, pz, they all commute unless it's two x's, two y's, two z's that are coming together, one as a position operator, one as a momentum operator. So, any two momentum operators commute, so that term goes away. Now, I pull the px out, so I get y pz z commutator px what's the commutator of pz and z? Minus ih bar. We know the canonical commutation relations, so that's minus ih bar right there. So I'm going to get minus ih bar ypx. Oh, that's a piece of LZ, isn't it? That's a piece of the LZ operator. In fact, what we're going to show is that Lx, Ly's commutator is minus is ih bar times Lz. So the nice thing is these guys commute to the other one. That's what it comes down to, times ih bar. But continuing along our merry way here, you know, at this point I think I'll probably say the reader can show, so plus dot dot dot. So you do all those other expansions, and the only thing else that doesn't die is x commutator of z with pz times py. So there is going to be such a piece that comes out of this term right here. You're going to pull an x out to the front. You'll have z commutator with pz and a py. Everything else is going to have commutators that vanished in it. So that's another minus ih bar right there. No, that's not. That's a plus ih bar, because it's a z commuting with piece of z. So in the end, what I'm going to get is minus ih bar, well no, I'll just put is equal to plus ih bar times x py minus y px. Plus ih bar x py minus y px. But that is the z that is the z component of the angular momentum right there. This operator is the operator representing L sub z. So glory be, Lx and Ly commute to ih bar Lz. Oh, actually, right, that was an accident. Glory be, Lx and Ly commute to ih bar Lz. And that's a y. And cyclic permutations. In other words, you can convince yourself that they can hop around. So, in other words, if everybody shuffles one to the left or one to the right, you get another valid commutation relation. So, if I make x move over here, y takes its place, z takes y's place. So they do kind of like a little dance, you know. So the guy on the end shuffles over here, and then the other guys move two over. Then you find that Ly, Lz commute to ih bar Lx. Do it again, and you find that Lz, Lx commute to ih bar Ly. So there's this happy cyclic permutation, commutation relation. Wow, it's a happy cyclic permutation, commutation, no relation, something like that. Yeah. It's glorious!